Welcome back to QHSE Talks. Right now, a worker out there is taking a single step across a perfectly flat, perfectly clean concrete floor.
Just a totally normal step.
Exactly, just walking. But in exactly 1.2 seconds, that one mundane step is going to cost their company like $50,000. And even worse, it could cost that worker their mobility for the rest of their life.
Yeah, it's a terrifying reality.
It really is. So today on QHSE Talks, we are unpacking the biomechanics, the physics, and the really grim realities of slips, trips, and falls. Because if you were preparing for the Associate Safety Professional exam specifically, we're talking about ASP 11 Domain 2, Topic 8, Part C. You aren't just memorizing some trivia here.
No, absolutely not. You're learning how to literally engineer gravity out of the equation.
Right. And, to do that, we are synthesizing this really intense stack of technical literature today.
Yeah, we're pulling from the ASP and CSP exam prep blueprints, some of the Bowen EHS practice materials, the Handbook of OSHA Construction Safety and Health, and even some advanced biomechanical engineering texts.
Which sounds super dense, I know.
It is dense. But our objective for you today is to take all that regulatory jargon, all those kinetic energy equations, and the limits of human physiology, and basically translate them into actionable, life-saving strategies for the safety professional.
Because walking is, it's something we consider so elementary, right? We do it while we're texting, while drinking coffee, holding conversations.
Oh yeah, totally on autopilot.
Right. But from a biomechanical standpoint, human walking is this miraculous, really precarious balancing act. It is essentially a continuous state of falling forward and catching yourself.
That's a great way to put it, falling and catching.
Yeah, your brain is constantly running these incredibly complex calculations. It's using your inner ear's vestibular system, your visual cortex, the proprioceptors in your ankles.
Just a massive amount of data processing.
All just to keep your center of mass hovering over a base of support that is rapidly moving.
And, the human brain has evolved to become so efficient at this process that it pushes the entire act of walking right into our subconscious. We suffer from what is basically profound biological complacency.
Biological complacency. I like that. We just take it for granted.
We do. But when you take that subconscious, evolutionarily adapted gait and you place it into a modern industrial setting.
Which is not natural at all.
Right. A setting filled with artificial polymers, maybe microscopic layers of machine oil, fluctuating elevations, unpredictable obstacles.
Some minefield, basically.
Exactly. The environment introduces variables that our physiology simply cannot react to fast enough. So to stop a worker from hitting the ground, we have to look past this surface level assumption of, clumsiness and actually deconstruct the epidemiological data.
We have to look at the statistical reality of gravity because, if we're going to understand why the Board of Certified Safety Professionals weights this domain so heavily on the exam, you've got to look at the numbers. And the numbers paint a brutal picture.
They really do. And these numbers aren't just data points. They are the starting line for any root cause analysis you're going to do.
So let's get into the data. What are we looking at?
Well, according to the Bureau of Labor Statistics data from 2022, there were 5,486 total workplace fatalities across all sectors.
Over 5,000. Wow.
And work-related falls accounted for 15.8% of those deaths.
Okay, so nearly 16%.
Right, which equates to 865 workers who suffered fatal kinetic impacts.
865 lives lost? That's heavy.
It is. But for the safety professional analyzing this data, the subcategorization is where the true narrative really emerges. So out of those 865 fatalities, 13.1%, which is 721 people, died from falls to a lower level.
Which makes sense, falling off a roof or a scaffold.
Exactly. But crucially, 2.6%, which is 144 fatalities, were caused by falls to the exact same level the worker was already standing on.
Wait, I really want to emphasize this. 144 people died tripping or slipping on flat ground.
On completely flat ground.
That is insane to me because when we think of workplace fatalities, we usually imagine, crane collapses, trench cave-ins, high voltage arc flashes.
The big dramatic events.
Yeah. The idea that a worker can lose their life simply traversing a flat hallway is deeply unsettling.
And you have to remember, fatalities only represent the absolute extreme end of the severity spectrum, right?
Yeah.
The frequency metrics are what truly paralyze an organization's operational readiness.
Right. The injuries that don't kill you but cost a fortune.
Exactly. Slips, trips and falls drive approximately 20% of all workers' compensation claims across the industrial spectrum.
1/5 of all claims.
And they generate 15% of all disabling injuries, meaning injuries that permanently alter the worker's physical capacity.
So they are never the same again.
Right. And when you isolate fall to same level incidents, they account for a staggering 69% of all injuries within the fall category.
Okay, wait. 69% of fall injuries are happening on the same level, not off a ladder.
Not off a ladder,
Yes.
just walking across the floor.
I mean, I look at those metrics and I see this invisible tax being levied against a company's workforce and its capital. 20% of workers' comp costs is an operational hemorrhage.
It's massive. It drains resources fast.
If a specific model of, say, a CNC machine or a forklift was injuring workers at that rate, the manufacturer would be forced into a global recall.
Oh, absolutely. The machinery would be locked out, tagged out, re-engineered immediately.
But because the mechanism of injury is just a human foot striking a power cord or, a shoe losing traction on a wet tile, it just gets written off as a behavioral anomaly.
People just say, oh, they were being clumsy.
Exactly. Watch your step, Bob.
And that assumption that the worker was simply being careless, that is the absolute hallmark of an immature safety culture.
Totally agree.
In advanced safety engineering, clumsiness is just an unacceptable root cause. You can't put that on an incident report.
Right, it doesn't actually solve anything.
Exactly.
Yeah.
We operate on the principle that humans perform as their environment dictates. If 69% of fall injuries are happening on the same level, there's a fundamental friction in the interface between the worker's biomechanics and the facility's design.
So there's a flaw in the system, not just the person.
Precisely. And to disrupt that failure loop, the safety professional really has to master the distinct physical mechanics of a slip versus a trip, because they are entirely separate kinematic events.
Yeah, let's pull those two mechanisms apart, starting with trips. If we look at the vector dynamics of a trip, what is actually happening in those milliseconds between the foot strike and the worker hitting the ground?
Well, a trip is basically a kinematic interruption. So consider the mechanics of your normal stride.
Yeah.
Your body's center of mass is projecting forward at your walking velocity.
Okay.
Your leading foot swings out to establish a new base of support, right, to catch that forward momentum.
Because, like we said earlier, walking is just controlled falling.
Exactly. But in a trip, that swinging foot encounters a physical obstacle. Maybe it's a protruding floorboard, a curled up anti-fatigue mat, or an improperly routed pneumatic hose.
Something that shouldn't be there.
Right. And suddenly the foot is violently anchored in place.
But inertia demands that an object in motion stays in motion. The foot has decelerated to zero, but the torso, the head, the center of mass, they're all still traveling at 3 or 4 miles per hour.
Exactly. The worker's body effectively becomes a lever.
Oh, wow.
Yeah, the anchored foot acts as the fulcrum, and the forward velocity creates rotational momentum. The center of gravity arcs over and past that fulcrum point.
Because the foot is trapped.
Right. Because the leading foot is trapped and cannot step forward to reestablish the base, the worker is thrown into an unrecoverable forward rotation.
A forward fall.
Yes. And this is why trip injuries so frequently involve fractures of the distal radius or the carpal bones. The worker instinctively throws their hands out and they end up absorbing the entire kinetic energy of the fall through their wrists.
Man, that makes so much sense. It's like hitting a sudden pause button on your feet while your torso is still on fast forward.
That's a perfect analogy.
And the hazards that cause this are often these tiny environmental changes that the brain simply filters out as background noise.
Yeah, we just don't see them.
Cluttered stairways, maybe an open file cabinet drawer, or even personal protective equipment itself, like an oversized coverall cuff catching the toe of the opposite boot.
Yeah, that happens all the time.
It is an abrupt mechanical blockade, so that's a trip. But if a trip is hitting a physical blockade, a slip is an entirely different failure of physics, right?
Completely different. A slip is a failure of tribology, which is the science of interacting surfaces in relative motion.
Tribology. Great word for the exam, by the way.
Definitely write that down. So a slip is the sudden, catastrophic loss of expected friction between the shoe's outsole and the walking surface. In a trip, the foot stops. But in a slip, the foot rapidly accelerates.
The phrase expected friction is incredibly revealing there. It implies that walking is a predictive act.
Oh, it is entirely predictive. The human brain calculates the coefficient of friction, or mu, based heavily on visual cues.
So our eyes are basically doing math before we take a step.
Exactly. If you walk toward a sheet of ice, your visual cortex registers that high-gloss surface. It signals your musculoskeletal system that the coefficient of friction is extremely low, maybe around 0.1.
And your body automatically compensates.
Right. Shorten your stride, you strike with a flat foot rather than the heel, and you tense your core to keep your center of mass directly over your feet.
But what happens when the visual cues lie to you? Let's say an industrial floor is made of polished concrete, and your brain anticipates a standard dry friction coefficient of around 0.5.
You're going to take a normal confident stride. Your heel strikes the ground at an angle, applying both downward force and forward shear force.
But if there is a hidden contaminant on that floor, like a microscopic layer of silicone lubricant or condensation or even fine granular dust,
then the actual coefficient of friction might be 0.05. When the heel strikes, the expected static friction is not there to resist the shear force.
it's like someone suddenly replacing the ground with a treadmill running in reverse.
Basically, yeah. The foot transitions instantly into kinetic sliding friction. The foot shoots forward and outward, and the center of mass is suddenly left suspended behind the base of support.
And physiologically, the body simply isn't fast enough to correct it, right?
No, not even close. The inner ear's vestibular canals will register the sudden drop in elevation and the backward tilt. But by the time that neurological signal travels to the spinal cord and commands the muscles to adjust.
The point of no return has already been crossed.
Exactly. The lag in that neuromuscular feedback loop is fatal in a slip. Because the legs fly out forward, the torso rotates backward.
So you're falling backward instead of forward.
Right, and the worker has no ability to brace. The impact is almost entirely absorbed by the sacrum, the thoracic spine, or worse of all, the occipital bone at the back of the skull.
That is terrifying.
It is. This is exactly why slips on the same level generate such a high severity rate of traumatic brain injuries and spinal cord contusions.
Okay, so if the human brain is constantly miscalculating this invisible friction variable, and our reaction times are just inherently too slow to overcome the physics, how do we engineer the environment so gravity doesn't win?
That's the core job of the safety professional.
Because, we can't just pave an entire pharmaceutical plant or food processing facility in heavy grit sandpaper. We have to look at the hierarchy of controls.
Right. And engineering controls are the baseline defense. The objective is to stabilize the coefficient of friction across the entire operational environment.
So, modifying the environment itself before we even talk about the worker.
Yes. OSHA's structural requirements mandate specific environmental interventions.
Yeah.
So, if a facility has continuous liquid processes, the engineering control isn't just handing out mops, It is altering the fluid dynamics of the room.
How so? Like changing the floor?
Exactly. This means installing steel grating that allows fluids to drop below the walking surface, or engineering the concrete slab with specific drainage slopes, or applying epoxy floor coatings that are actually embedded with aluminum oxide grit to physically lock into the tread of a boot.
That makes sense. Build the friction right into the architecture. But engineering controls have their limits, right?
They do.
You can install all the floor drains in the world, but eventually you are relying on the human beings operating within that space to interact with it safely. Which brings us to administrative and behavioral controls, essentially altering human performance.
And this is where we see the deployment of specific PPE, like slip-resistant footwear.
Which seems basic, but I bet it's not.
Far from it. For a safety professional, it is never enough to just mandate non-slip shoes in the employee handbook. You must understand the material science of the environment.
Give me an example of how that goes wrong.
Okay, so a boot with a soft polyurethane outsole might provide incredible grip on a dry, dusty warehouse floor. But if you take that exact same polyurethane boot into a machine shop with petroleum-based cutting fluids on the floor,
It's not going to work.
the chemical composition of the oil will actually degrade the sole, and it will hydroplane instantly.
Oh, wow. So it literally creates a hazard.
Yes. In that environment, the worker requires a high-density nitrile rubber compound, and it needs wide tread channels designed to aggressively disperse those viscous fluids away from the contact patch.
Okay, so the PPE has to match the specific tribological hazard.
Precisely.
But beyond what the worker wears, there is this deeply uncomfortable challenge of training them on how to move. You see behavioral training materials suggesting workers should point their feet outward, slightly bend their knees, and take shorter strides.
Ah, yes, the so-called penguin walk.
Yeah. I have to be honest, as a safety professional, standing in front of a room of master electricians or heavy equipment mechanics and telling them how to place their feet feels incredibly patronizing. Like, really? grown adult.
It is one of the most delicate communication challenges in the profession. I completely agree. If you approach a veteran workforce and simply dictate that they must waddle like a penguin, you will lose their respect instantly.
Right, they'll just laugh you out of the room.
They will. The approach must be rooted in biomechanics, treating the workers as intelligent professionals. You don't just tell them to point their toes out, you explain the math.
Okay, how do you explain the math of a penguin walk?
You explain how widening the stance increases the lateral base of support. Mathematically, that reduces the chance of a rotational fall.
Got it. Give them the why, not just the what.
Exactly. You explain the physics of the knee joint, acting as a biological shock absorber, keeping the center of gravity low, and preventing the torso from acting as a lever.
Right, going back to that trip fulcrum we talked about.
Furthermore, you have to explain the biomechanical necessity of keeping their hands out of their pockets.
Oh, this is a huge one, especially in cold weather.
In a cold environment, workers naturally pocket their hands. But the human arms are essential counterweights.
Because they need to balance.
Right. When a slip initiates, the involuntary flailing of the arms is actually the body's desperate attempt to aggressively shift its center of mass and regain equilibrium.
It's like a tightrope walker with that long pole.
Exactly like that. But if the hands are trapped inside a jacket pocket, that rotational torque is completely eliminated.
They can't counterbalance at all.
Right.
Yeah.
And the head and shoulders take the full velocity of the impact. So when you explain the physics of a crushed skull versus a sprained wrist, the behavioral modification becomes logical rather than patronizing.
Yeah. Suddenly taking your hands out of your pockets isn't a silly rule. It's armor for your brain.
Exactly.
And we really cannot discuss behavioral controls without addressing the most foundational and honestly often most dismissed control in the industrial playbook: housekeeping.
Housekeeping, yes.
I think there is a really dangerous misconception out there that housekeeping is just a janitorial function. You know, that it's just about making the facility look presentable for when corporate visitors show up.
That is a terrible mindset. In safety engineering, housekeeping is an aggressive form of entropy management.
Entropy management? That sounds way cooler than sweeping.
Right. But seriously, when tools are left out, when extension cords are strung across walkways, or when pallet wrap is left on the floor, the organization is actively injecting unpredictable variables into the worker's expected environment.
Which ruins all those subconscious friction calculations we talked about.
Precisely. Poor housekeeping is legally cited by OSHA as a primary root cause of tripping hazards. Tolerating a cluttered workspace is a systemic failure. It tells the workforce that unsafe conditions are the acceptable baseline.
It is the industrial equivalent of the broken windows theory.
Exactly.
If you ignore the puddle of hydraulic oil today, you are normalizing the condition that will fracture a femur tomorrow.
Couldn't have said it better myself.
All right, so everything we have analyzed so far assumes the worker's boots are firmly on the ground. But the dynamics, the regulations, and the severity indices shift violently when we introduce elevation.
They absolutely do. When a worker leaves the ground, the margin for error effectively drops to zero.
So let's talk about heights. For the ASP exam, you must intimately understand the threshold triggers for the OSHA 1926.501 standard.
Yes, the fall protection standard.
Right. In the construction industry, the absolute duty to have fall protection initiates when a worker is on a walking or working surface with an unprotected edge that is 6 feet or more above a lower level.
6 feet. That is the magic number.
But 6 feet. Honestly, to the average person, 6 feet of elevation doesn't sound like a catastrophic height. I mean, you can jump off a 6-foot wall as a kid and be perfectly fine. Why is OSHA so uncompromising at this specific threshold?
Because the physics of human reaction time and terminal impact are entirely unforgiving. It takes approximately 0.6 seconds for an object to fall 6 feet.
Barely half a second.
Right. Now, the average human physiological reaction time to an unexpected event is roughly 0.25 to 0.3 seconds.
Okay, so doing the math there.
By the time the worker's brain even registers that the center of gravity has been lost, half the fall distance is already gone. They strike the ground before their musculature can even tense up to absorb the impact.
Wow, so they hit completely unprotected, neurologically speaking.
Exactly. We have to move past the old, tired cliche that it's not the fall that kills you, it's the sudden stop.
Right. People say that all the time.
It really minimizes the extreme violence of a vertical deceleration. Let's compare a fall from height to dropping a water balloon.
Okay, a water balloon.
When the human body strikes the concrete, the skeletal structure stops moving in an instant. It hits zero velocity. But the internal organs, the brain, the heart, the liver, They're suspended in fluid and connective tissue inside the body.
Oh man, I see where this is going.
They're still traveling at the velocity of the fall.
So the body stops, but the organs keep falling.
Yes. That internal momentum is what generates massive internal trauma. The aorta, for instance, is tethered to the spine, but the heart itself has mobility within the chest cavity.
Okay.
Upon sudden deceleration, the shearing force can literally tear the aorta away from the heart, causing massive internal exsanguination in seconds.
That is horrific.
It is. Similarly, the brain continues forward, striking the inside of the skull, then rebounding and striking the opposite side. That's a coup contra coup brain injury.
Yes, from the brain sloshing inside the skull.
Right. The human body just has no physiological mechanism to withstand a deceleration from 20 miles per hour to 0 in 3 milliseconds.
Which is exactly why the regulatory framework for working at heights is built on the 4 goals of fall protection. Let's list those out for the listeners. First, prevent people from falling. Second, prevent objects from falling. Third, reduce the energy levels if a fall does occur. And fourth, reduce the injury at impact.
Right. And as safety professionals, our entire focus should be aggressively weighted toward those first 2 goals. Because if we achieve those, the kinetic energy calculations of the last 2 never become necessary.
Absolutely. Stop the fall before it happens. But let's look at that second goal really quick, preventing objects from falling. This addresses the critical struck by hazard.
Yes, falling objects. Because gravity applies its acceleration equation, 9.8 meters per second squared, equally to a human body and a dropped tool.
Okay, let's quantify that danger for our ASP candidates. Say we have an iron worker. They are 50 feet up on a steel structure, and they drop a standard 2-pound spud wrench.
Just a simple tool slip.
Right. That tool accelerates rapidly. By the time it reaches the ground, the potential energy has converted to kinetic energy. The wrench is traveling at over 50 feet per second.
A missile, basically.
Yeah. And when the narrow steel edge of that wrench strikes a worker below, the force is concentrated over a microscopic surface area.
That concentrated force easily exceeds the polycarbonate shell resistance of a standard ANSI Type 1 hard hat.
Really? It just goes right through?
Yes. The impact will shatter the helmet and penetrate the skull. So to mitigate this, safety professionals must engineer controls specific to the struck-by hazard.
What kind of controls are we talking about?
Well, this includes installing rigid toe boards along the edges of all elevated platforms. That prevents debris from just being kicked over the edge.
Right. Simple but effective.
It also requires erecting canopy structures equipped with heavy-duty, quarter-inch woven wire mesh above walkways to catch falling materials.
Kind of like those covered sidewalks you see around high-rise construction.
Exactly. And it demands the establishment of strict, barricaded fall zones below elevated work areas. And those zones have to be mathematically calculated based on the deflection radius of a falling object.
Because it doesn't just fall straight down. It can hit a beam and bounce outward. But, when we cannot eliminate the fall hazard entirely, and we cannot use passive physical barriers like standard 42-inch guardrails, we cross a terrifying threshold. We move away from preventing the fall, and we accept that the fall is probably going to happen.
Which is a huge mental shift.
It is. We transition to relying on personal fall arrest systems, harnesses, lanyards, and anchor points.
And this is exactly where the safety professional must transition from an administrator to a kinetic engineer.
Time to do some math.
Oh, yeah. Domain 1, Topic 7 of the ASP exam blueprint requires you to calculate fall protection parameters. And listen to me. You cannot approximate these variables.
No guessing allowed.
Absolutely not. A mathematical error here is not just a theoretical failure on a test. It is a direct cause of a fatality in the real world. You must precisely define and calculate the free fall distance, the maximum arresting force, the total fall distance, and the required clearance below the worker.
Okay, let's run a live calculation then. I want to tackle the specific scenario outlined in the Bowen EHS study sources, because this is exactly how the exam will test your understanding of deceleration physics.
Let's do it. Walk me through the scenario.
All right, we have an iron worker. They are 6 feet tall. They are working on a second-level open deck, which is exactly 12 feet above the concrete ground.
Okay, 12-foot deck.
Right. They are wearing a full-body harness. They are tied off using a standard 6-foot lanyard, which includes a 3.5-foot shock-absorbing device.
Got it.
Now, here's the kicker. The lanyard is anchored directly at their feet, right at the deck level. The critical question for the safety professional taking this exam is, does this specific configuration prevent the worker from striking the lower level?
Okay, let's process the math linearly. So the worker slips and steps off the edge of that 12-foot deck. Because their anchor point is at their feet, they will experience a free fall exactly equal to the length of their lanyard before the system applies any arresting force.
Okay, so the lanyard is 6 feet long, so they free fall 6 feet.
Right, they have dropped 6 feet. The lanyard snaps taut. Now, if this were a static steel cable, the sudden stop at this velocity would simply snap their spine.
Because of the sudden deceleration.
Exactly. But it's not a static line. The shock absorber initiates.
Okay, so how does that work mathematically?
Well, the maximum arresting force allowed by OSHA on a human body is 1,800 pounds, or 8 kilonewtons. To keep the force below that lethal threshold, the kinetic energy must be dissipated over time and distance.
How does the lanyard do that?
The shock-absorbing lanyard is constructed with folded webbing stitched together with specialized threads. As the lanyard goes taut, these threads begin to snap, tearing the webbing apart stitch by stitch.
Oh, so it's physically breaking apart to absorb the energy.
Yes. This physical destruction of the material converts the kinetic energy of the fall into thermal and deformation energy, safely decelerating the worker.
Got it. So the shock absorber tears open, adding its fully deployed length to the fall. That is 3.5 feet. Okay, let me run the numbers. We have the 6-foot lanyard. We add the 3.5 feet of the deployed shock absorber. That is 9.5 feet of total drop so far.
With you.
The deck is 12 feet high. 9.5 is less than 12. So the system works, right? They don't hit the ground.
And that right there is the exact mathematical trap that kills workers.
Wait, what did I miss?
You have calculated the distance to the hardware, but you've completely forgotten the physiology of the human attached to it. Where is that lanyard anchored to the worker?
Oh, it's attached to the dorsal D-ring on the back of the harness, right between the shoulder blades?
Precisely. The D-ring is now suspended 9.5 feet below the anchor point, but the worker's legs hang beneath that D-ring. For a 6-foot-tall worker, the distance from the D-ring down to the soles of their heavy work boots is roughly 5 feet.
Oh man, we have to add that 5 feet to the equation.
We absolutely do. Furthermore, nylon webbing is not rigid. Under the dynamic load of a falling human body, the harness itself will stretch and pull upward. We must factor in at least 1 foot for harness stretch.
I see the catastrophic error. Let me recalculate.
Go ahead.
We have 9.5 feet for the equipment drop. We add the 5 feet from the D-ring to the boots. We add 1 foot for harness stretch. That brings the total fall distance to 15.5 feet.
Yep, 15.5 feet.
The bottoms of their boots will be 15.5 feet below the anchor point when the system finally arrests their momentum. But the deck is only 12 feet above the concrete.
They strike the ground.
They hit the concrete with 3.5 feet of unarrested deceleration left in the system. The shock absorber hasn't even finished deploying.
Exactly. The worker takes the remaining kinetic energy directly into the skeletal structure. In a real-world scenario on a 12-foot deck, handing this worker a standard 6-foot shock-absorbing lanyard is effectively providing them with a 15-foot rope to hit the ground.
That is wild. They think they're safe, but they're basically wearing a placebo.
It's tragic. That is why this calculation is the dividing line between a certified safety professional and someone who just hands out PPE from a supply closet.
It's a huge distinction.
If you do not calculate the required clearance, which, by the way, also dictates adding a 2-foot safety factor buffer to your final number, you are engineering a full sense of security.
So what should the safety professional have done in this scenario?
In this environment, they needed to intervene early. They needed to implement a higher anchor point above the worker's head to eliminate that initial 6-foot freefall. Or utilize a self-retracting lifeline that senses acceleration and locks the fall within inches rather than feet.
Because this math equation is not a theoretical exercise. It is the literal distance between a worker hanging in a harness waiting for a rescue team and a trauma helicopter landing on the job site.
It's life or death, plain and simple.
Which brings us to a broader perspective, I think. We've analyzed the epidemiological data of same-level falls. We've deconstructed the tribology of slips and the vector mechanics of trips. We've mathematically calculated the brutal physics of fall arrest systems.
We've covered a lot of ground.
We really have. But how does the safety professional integrate all of this technical engineering into the broader architecture of a corporate safety management system?
Well, it requires a transition from granular engineering to systemic management.
Give me an example.
Okay, for example, OSHA allows for the use of safety monitor systems under very strict, limited parameters where conventional fall protection is demonstrably unfeasible or creates a greater hazard.
What exactly is a safety monitor?
A safety monitor is a competent person whose sole function is to act as a human guardrail.
But relying on human attention as a primary safety control, I mean, that seems deeply flawed. The regulations state the monitor must be on the same level, within visual sight, close enough to communicate orally, and they can have absolutely no other distracting responsibilities. They just stand there and watch the other workers.
Right. And from a psychological standpoint, it is a highly compromised system.
Why is that?
Human beings are biologically incapable of maintaining sustained, absolute focus on a passive environment. It is a psychological phenomenon known as vigilance decrement.
Vigilance decrement.
Yes. After 15 to 30 minutes of watching coworkers perform routine tasks, the monitor's brain will naturally begin to filter the scene as non-threatening background information. Their attention drifts.
Because nothing is happening.
Exactly. They check their watch. They look at a piece of machinery. A bird flies by. And in that 3-second lapse of attention, a worker takes a step backward off the leading edge.
And it's over, which is exactly why administrative controls are the absolute weakest link in the hierarchy. You simply cannot engineer out human fatigue or distraction.
You can't. And when those controls inevitably fail, the safety professional's role shifts rapidly into incident investigation and workers' compensation management.
Let's talk about that investigation phase.
The investigation of a fall is not an exercise in assigning blame. It is a forensic audit of the safety management system.
Okay, so if a worker slips on a fluid spill, you don't just write, "floor was wet," on the form.
No, the safety professional uses techniques like the 5 whys to dig into the operational failure. Why was the floor wet? Because the valve leaked.
Yeah.
Why did the valve leak? Because preventative maintenance was deferred.
Why was it deferred?
Because the procurement department delayed purchasing the replacement seals to save budget for the quarter.
Oh, wow. So suddenly a slip and fall injury is traced all the way back to a systemic supply chain failure in a totally different department.
Exactly. And tracing that failure is vital because the financial ramifications of these incidents dictate the company's ability to operate.
And the study materials really emphasize this. They talk about the concept of the experience modification rate, or the EMR. How does a single fall impact the massive actuarial baselines of a corporation?
Well, think of the EMR as the financial scorecard of an organization's safety culture. Insurance underwriters calculate a company's historical injury data, weighing both the frequency of incidents and the severity of the medical costs, and they compare it against the actuarial average of their specific industry.
Okay, so it's a baseline.
Right. An EMR of 1.0 means your company is exactly average, and you pay standard workers' compensation premiums.
But if your facility accepts poor housekeeping as normal, and you have a high frequency of trips resulting in, say, torn rotator cuffs and spinal surgeries, the actuarial math shifts against you.
Precisely. If your severity metrics push your EMR up to 1.25, your organization is now paying a 25% surcharge on its insurance premiums.
A 25% penalty.
Yes. And for a massive industrial contractor, that can equate to hundreds of thousands or even millions of dollars in lost capital annually.
Just evaporating.
And it gets worse. A high EMR can also disqualify a contractor from even bidding on lucrative government or private projects. A lot of clients won't let you on their site if your EMR is over 1.0.
So it literally stops the company from making money.
Exactly. So the safety professional uses this actuarial reality as leverage. When you go to management and request a $50,000 capital expenditure to mechanically scarify and recoat a high-risk polished floor, you aren't just asking for a safety budget.
Right, you're not just saying, please make it safe.
You are presenting a financial strategy to reduce the EMR and protect the company's profit margins.
That is how you speak the language of the C-suite. But, the physical modifications and the financial metrics are completely useless if the workforce doesn't understand the operational hazards. The final layer of the safety system has to be the duty to train.
Training must be an interactive feedback loop, not just a passive lecture where someone reads PowerPoint slides in a dark room.
We've all been in those meetings. They don't work.
They don't. Workers must be trained to continuously evaluate the coefficient of friction in their environment. They must be intimately trained on the deployment mechanics and the inspection protocols of their personal fall arrest systems.
Right, they need to know what to look for.
Exactly. They must know how to check the webbing for UV degradation, chemical burns, or frayed stitching before they ever clip into an anchor point. Because if they don't know the equipment is compromised, the physics won't save them.
Man, this has been an incredibly dense and critical session of QHSE Talks.
We really went through it.
Yeah, we did. We began by staring down the grim statistical footprint of same-level falls, that horrifying 69% injury rate that plagues our industries.
Yeah, the invisible tax.
We dove deep into the microscopic tribology of expected friction and the physiological limitations of the human vestibular system during a slip. We scaled the structural steel to understand the unyielding physics of a 6-foot drop and the lethal force of a struck-by impact from a simple hand tool.
We performed the life-or-death mathematics of deceleration, proving exactly why failing to account for harness stretch and D-ring placement will result in a worker striking the ground even when wearing the proper equipment.
Which is still blowing my mind. And we connected these granular engineering concepts to the macro-level financial reality of the experience modification rate and corporate safety systems.
It's all connected.
Mastering these technical, biomechanical, and mathematical elements is the absolute key to conquering ASP 11 Domain 2 Topic 8 Part C. But listen, the exam is merely the gateway. Passing the test just proves you can perform the calculations on paper.
Right, the real world is much harder.
Your career will test whether you have the conviction to implement them in the field, especially when production schedules are tight and budgets are restricted.
Because the laws of physics are completely immune to negotiation. Gravity does not care about an organization's production quotas. It only responds to the physical controls and the engineering parameters that the safety professional puts in place.
As we conclude this analysis, I want to leave you with a final perspective to carry on to your job site tomorrow. Think about the massive chasm between human evolutionary biology and modern industrial design.
Oh, that's a fascinating angle.
Right. Because for hundreds of thousands of years, the human musculoskeletal system evolved to navigate uneven organic terrain. We evolved to walk on dirt, rocks, and mud, constantly adapting to minor shifts in elevation.
Natural environments.
Exactly. We did not evolve to spend 10-hour shifts walking on perfectly flat, artificially leveled concrete coated in synthetic polymers.
No, we definitely didn't.
Yeah. And we certainly did not evolve to operate heavy machinery while suspended on a 4-inch steel beam, 100 feet in the air, relying on a woven nylon strap to override our biological vulnerability to gravity. Our brains, our reaction times, and our kinetic instincts are operating completely out of context in the modern industrial environment.
It is a complete evolutionary mismatch.
Exactly. So, as a safety professional, your fundamental duty is not simply to cite OSHA regulations or file compliance paperwork. Your job is to recognize this evolutionary mismatch. Your job is to aggressively engineer environments, calculate physical tolerances, and build protective systems that shield fragile human biology from an unforgiving industrial world we simply were not built to survive in on our own.
That is the true core of the profession.
Thank you for dedicating your time to this extensive analysis. Respect the physics, master the math, and we will see you next time on QHSE Talks.